Hi all, today we're just going to be going over the group work, which is actually kind of a review, the recitation group work that's actually kind of a review for the chapter 7, 8, and 9 exam. So we're going to focus a lot more heavily on 7 and 8 and then more lightly on chapter 9 for this exam. But this is a list of everything that you'll need to know if you're in my class or Dr. Corrales' class for this upcoming exam. So if you want to stop and look over a review of that, that's a good overview. Okay, so for this first question, when I see, I've mentioned before, whenever I see a reaction and I don't know what it's going to be about, I ask myself, is this an acid-base reaction? If it's not, then is it a substitution or elimination reaction? And if it's not, then is it something we learned from chapter 8? So first, does this look like an acid-base reaction? This doesn't look like an acid-base reaction to me because there's no acidic hydrogens available really anywhere. There's nothing that wants to give up a proton. All the pKa of all this is like 50, so that's probably not going to do anything. The next question, substitution elimination, well, there is a good leaving group and there is a strong nucleophile. So that tells me this is probably going to be a substitution or elimination. And because it's a strong nucleophile, OET minus, that lends towards the 2 side of the folder, right, of the decision tree. It's going to lead to the 2 side. So that strong nucleophile is going to put us to the 2 side of the decision tree. It'll be either an SN2 or an E2. And heat will automatically make me go to E2 every time. So this is going to be an E2 reaction. And one thing we know about E2 reactions is it needs to be anti-periplanar. So we have to check for that. So in this case, if we have our bromine going straight up, we learned that it'll alternate axial, equatorial, axial, equatorial. So if this was a wedge, it would be equatorial, which means if this is axial, this wedge would be equatorial. So then the hydrogen is right there, or the CH3 group right there must be axial. Well, for anti-periplanar for hexane rings is also called coaxial. So if you have a bromine pointing up right there at this corner, at one of these 2 points, you need to have a hydrogen, either at carbon 2 or carbon 6, whichever one has an axial hydrogen. And if they both, then you go to Seytzef-Hofmann rule. But actually, the CH3 is axial here, so the CH3 will be axial on carbon 2, which means that there's not an axial hydrogen there. So a double bond can't form from here. This hydrogen can't be taken because this hydrogen is equatorial, not coaxial. So if the bromine's pointing axially up, the hydrogen needs to point axially down. And there's no way a hydrogen can point axially down here because it's not a CH3. So on this carbon, however, there's a hydrogen both in the axial and the equatorial position. So easily we have a hydrogen in the position we want for carbon 6. So I know because this is the only one that has a coaxial hydrogen or anti-periplanar, that this is going to be able to come take one of those hydrogens. It'll take the wedge, fill in the electrons right there, and then the leaving group will leave. So that means our double bond will form right here, and the bromine will have left, and there's still a CH3 dash over on the far side. Oh, I did not do all this. So the first step A was draw the chair conformation. I was just explaining how I approach it. But so if you have your bromine pointing up, you need a hydrogen here or a hydrogen here. We didn't have a hydrogen here. That was a CH3, so we couldn't have it form right here. The double bond had to form here. So that's how we found the periplanar hydrogen. And then this is the final product. So that's how I got to that answer. Okay, predict the products of the given reaction. So again, is this acid-base? This doesn't look like an acid-base to me because there's not an easily available hydrogen. So then the next thing I'm going to ask myself is this a substitution or elimination? Well, there is a good leaving group and there is a good nucleophile, so definitely this is going to be substitution or elimination. This is strong, so if it's strong, it's going to go to 2, either E2 or SN2. SN2 is usually favored by more narrow nucleophiles, this is a bulkier nucleophile, so I think it's actually going to favor E2 because of the bulky nucleophile. Also, because of the bulky nucleophile, it's going to favor Hoffman product. So your hydrogen is going to be taken from over here, and then your leaving group will leave. So the product you would get would look like this. In this case, we didn't, even though it was an E2, we didn't have to worry about it being antiperiplanar because all three of these are the same substituent. So any of those hydrogens could be taken at the antiperiplanar position. But if you have an internal bond forming, you do need to make sure it's antiperiplanar. And that's actually kind of what's happening on the next question. How would this reaction be different if you use ethoxide? It's still a strong nucleophile. It's narrow, so actually with ethoxide, I think you would get a mixture of SN2 and E2. You would get some E2 as well, though, and it asks if you draw the final product, is it E or Z? So we want to see the elimination final product of this reaction. So here we go. And if we had ethoxide, you have ethoxide is going to give the more substituted product, the site F product. So if you had that, you need to make sure that when it abstracts from this hydrogen right here, forms a double bond and the leaving group leaves, it's antiperiplanar. So to do that, we draw a Newman projection. So I'm going to draw my Newman projection looking from right here. My iodine is a wedge. So if the hydrogen is coming towards me, the iodine is coming towards me, then when I look at it in the plane of the page, it's going to be on the right. So we have a CH3 pointing straight up and iodine coming towards me, and the implied hydrogen here is actually a dash. And then on the back carbon, you have your isopropyl group pointing straight down. I always do my plane of the page first. Your hydrogen is on the right, remember, because if it's coming towards you and then you turn it, it's on the right. And then the plane of the page is going away from you. If you turn it, that's on the left. So that would be your CH3 group. So you'll notice the iodine isn't across from a hydrogen, and it needs to be anti-periplanar for the elimination to take place. So actually, this is all going to rotate over one. So I'll keep the front carbon the same. So this is using what we learned from chapter 4 and 5 and bringing it into reactions and how the shape of reactions is going to impact really how the reaction proceeds forward and what product you get. So if you see all this rotate around, then you can know that the iodine and the hydrogen are going to be eliminated based on this mechanism. The hydrogen will be extracted. The lone pairs that used to make up this bond will fill in to make a double bond appear right here, and the leaving group will leave. So these two are covered up, and I like to literally, when I'm getting rid of the hydrogen and iodine, where my finger is the double bond. So above my finger, we have a methyl group and an isopropyl group. And below my finger, we have a hydrogen and a CH3. So if you cover those up, you can kind of see the double bond is right here where this pencil is. You have a CH3 and an isopropyl on top, a hydrogen and a CH3 on the bottom. And that's how you can find out if it's an E or Z product. So this is a higher priority on this side, and this is a higher priority on this side. So the overall final product should be Z because the higher priorities are on the same side. Okay. So for this next question, we're doing a hydroboration reaction. That's what I just have to tell you. It's hydroboration. And I'm going to go ahead and draw the mechanism down here. So I'll redraw this. And actually, I like to draw the BH2 on this side, the hydrogen's BH3. It lines up to the alkene, and the boron is going to go on the less substituted side because, you know, it's got more bulk around it, so it's going to line up where it has more space. And then the nucleophilic alkene is going to attack at that boron because it doesn't have a full octet. I'm going to try to zoom in a little bit here. I feel like it's hard to see. Okay. It doesn't have a full octet, so it does want electrons. So it's easy for the extra electrons around this alkene to attack. But actually, then simultaneously this double bond will come down here and you get a transition state. This is not an intermediate, so you don't have to draw this, but it helps me to visualize it, where your BH2 is on this side, your H is on this side. This bond is breaking, this bond is breaking, and these two bonds are forming, and it looks kind of like a square. But that's the transition state, and you'll end up with a BH2 on one side and a hydrogen on the other, and then you'll have your hexane, and these both add to the same side because the BH2 comes down on the same side, so you get syn addition. And then I guess we kind of drew this poorly. This is the alkene attacking, forming the transition state, and then you have the final BH2. And then BH2 is replaced with the hydroxyl group. You don't need to know how this happens, but you do need to know stereochemistry is retained. So you end up with this as your final product. Not only will you end up with this as your final product, but you also will have the mirror image of this because the syn addition can happen on either side. So this would be your final product. And if you want, you don't have to draw that hydrogen because technically it is implied, but I just like to draw it so you can see. Sometimes test questions will be tricky. Will they'll have a methyl group or something already there, and they'll kind of trick you by just, you'll see a wedge and a dash and think, oh, that's not hydroboration because it's not syn addition, but it is syn addition. They're just not showing the hydrogen, so you need to look out for that. Okay, this NMR question I think is kind of tricky, but we're going to go step by step, and I think that will help us. So label each peak and determine the number of hydrogen atoms represented. Well, there's one. I'm just going to say peak A, B, C, and D. And the ratio, the integral area under the curve is 1 to 1 to 2 to 6. And sometimes you'll have to double or triple this because it's just a ratio. It's not actually the number of hydrogens, but you can add it up and see if it adds up to the number of hydrogens in your structure to find out if you need to double it. Here we have 6, 7, 8, 9, 10, so we don't need to. So there's 1 hydrogen here, 1 hydrogen here, 2 hydrogens here, and 6 hydrogens there. Now, the splitting pattern for each peak is weird because actually it's 0. And when we talk about splitting patterns, each of these are a singlet. Singlets look like this. A doublet would look like this. A triplet has a tall peak in the middle. But the whole thing would integrate to the ratio of the number of hydrogens, right? So it would be as if this peak had 2 little points in it, not just one single point. But none of these have any splitting in them, which means there's 0 splitting. So normally the splitting pattern is n plus 1. So I guess not 0 splitting. They're 1 peak. They're a singlet. N plus 1 equals your splitting. But here your splitting is 1. There's just 1 peak. So n plus 1 equals 0. So, n plus 1 equals 1. Sorry, I keep doing that. So n must be equal to 0 because there's no splitting. That means there's no neighboring hydrogens to anything. And that's really tricky because how do you get a carbon structure where there's no neighboring hydrogens? Well, one thing I'll say is whenever you have an alcohol, if there's a carbon right next to it like this, that carbon is not going to have this splitting there would be no splitting from this hydrogen because the oxygen interrupts the splitting. So that alcohol there would probably be a hydrogen single peak with no splitting. And that's what A and B make me think, alcohol groups. So I automatically am thinking there's probably 2 alcohol groups. But then I'm thinking, how are there going to be 2 alcohol groups with 4 carbons and no splitting in between? And this 2 right here for carbon C makes me think there must be 2 hydrogens on 1 carbon, but then 6 hydrogens? We don't see 6 hydrogens on a carbon ever. So that makes me think there's 2 methyl groups with 3 hydrogens that are in the same environment. So if I were to use that logic to put a methyl group here and a methyl group here. These two methyl groups are in the same environment. Now we have 4 carbons, and this carbon doesn't have a hydrogen, so it won't split. Like this carbon right here is the neighbor to these 2 methyl groups, so there's no splitting because it doesn't have a hydrogen on it. And this carbon, it's the neighbor to these 2. It still doesn't have a hydrogen, so these don't have any splitting. So that's kind of a difficult question, I think, a kind of difficult NMR. If you got the basics and you knew that these were the integrals of hydrogen and you knew the splitting and then you got stuck on making the molecule, that tells me that you're on the right path. Initially, actually, when I even saw this, I thought it was a diol like this because I could tell it was a diol, and I knew there was 6 hydrogens in the same environment, and this is like a plane of symmetry right here. That doesn't really make sense because these would have had to be overlapped, but I was like, these would be splitting each other because there's a hydrogen right here and a hydrogen here, so these should be splitting, right? That's what I just kept thinking. It took me a while to come up with this structure. So if you're getting stuck on that structure, that's totally fine. That's normal. I would honestly almost expect it. So, but if you kind of are getting the basics down and you got to that point, you're on the right track. So don't give up or get frustrated. Okay, and then the very last question is a multi-step synthesis. So whenever, I'm going through these kind of questions, I always ask myself, acid base, there's no protons. It seemed like they want to give up, so no. And then a substitution or elimination, well, there's 2 good leaving groups. An NH2 minus is going to be a good nucleophile. And we learned that NH2 minus especially is used when you're trying to make an alkyne. So this hydrogen will still come here and kick out this leaving group, and you'll end up with an alkene with 2 hydrogens. And then this NH2 minus will actually do that again. Oh, you have a chlorine here too. And kick out your leaving group, and you'll end up with an alkyne. So that's actually for A. But then if you have, actually NH2 will go one more step here. If you have excess, and it'll take this alkene, or this alkyne, that pKa there, it becomes an acid-base question because that pKa is 25, and your structure for A will actually be, let me make sure I get the right number of carbons, this, but then you add water, and it can actually protonate that and add it back to make it a hydrogen. But you put it back in NH2, but this time only one equivalent of NH2. So you could have almost skipped that step. I think we just wanted to make sure you knew what happened if you put excess alkyne in there. So step 1 of this will give you back to generating the nucleophile, and then it'll attack on that methyl group and kick it out. It is actually another SN2 reaction. We did something like this, very similar to this on your last quiz. So when I looked at this one, I saw, is this an acid-base reaction? And my first thought was actually, yes, this is a pretty acidic proton. So it's going to take that proton and make this negatively charged. And then if I mix that negative charge in with the CH3Br, then that makes me think, is that going to be another acid base? No, there's not really an acidic proton. Substitution or elimination? Well, this is a strong nucleophile and this is a good leaving group. So yeah, probably a substitution. And we learned specifically about NaNH2 and using primary alkanes to get substitution reactions with these kinds of reactions. So we spent time specifically on this at the end of chapter 7. So you should hopefully start to be recognizing anytime you see NaNH2 minus and 2 leaving groups, that's going to get you a terminal alkyne if it's at the end. And if that terminal alkyne is exposed to NH2, it will deprotonate it. So hopefully you remember that. But then if we add that to palladium on calcium carbonate and quinoline, this is actually a poisoned catalyst. So not an acid-base reaction and not a substitution or elimination reaction. So then I asked myself, is it one of the other things we learned in chapter 7 and 8? And we learned about this to make alkenes. We learned that this palladium with calcium carbonate and quinoline and Lindlar's catalyst both are poison catalysts. So we talked about how alkene alkynes will go from alkenes all the way to alkanes really quickly. They don't naturally stop at any point. Just like when you're going down the stairs, you don't usually just stop for no reason, unless there's a reason. And the reason here is we have a poisoned catalyst. So someone's sabotaging the stairs and it's not safe to keep going down or whatever. That's kind of what we talked about in my class. So once you hit that poisoned catalyst, it's going to stop at an alkene. Then you have to ask yourself, is it going to make a cis or trans alkene? And actually, Lindlar's and this will both do cis alkenes, and then dissolving metal reduction, which is a metal with an H3. I can't remember the reagents off the top of my head, but dissolving metal reduction will give you trans. So this will be cis, and you'll have CH3, and then your 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And that'll be your final answer. So sorry, I went through that more quickly than I normally do. I forgot about this one on the back. Rats. Okay, I'm running a little late, but I want you guys to have this before your exam, so I'm going through pretty quickly. But when I see this, you have to do retrosynthesis. So I'm looking at these ketones, and I know the only way we learn to make a ketone like this is actually using O3, and that will cleave a ketone, or cleave a double bond into a ketone. And there's 6 carbons, so that plus this structure makes me think we had a ketone right here that got cleaved. 1, 2, 3, 4, 5, 6 carbons, and they're all connected to each other, so this must have been the cleaving point, cutting right through here. But also, there needs to be an isopropyl over here, because this has isopropyl, but on this side it's just hydrogen. So, okay, well, we have an alkene. How did we get an alkene? Well, if you're going from an alkene to this structure, is there a way to do that? And hopefully, there is a way to do that if you have a elimination reaction. But you need to make sure there's an anti-periplanar hydrogen to take before you decide what kind of elimination reaction. So we need some kind of elimination reaction that'll form an alkene right there. If you did an E2 elimination reaction, you actually don't have an anti-periplanar hydrogen right there. So you'd need to do an E1 reaction. So the leaving group would leave, and a carbocation would be formed right here. Well, a carbocation would be formed here, and then it would undergo rearrangement and form right there. And then if either one of these hydrogens is eliminated, you would get this alkene. So this alkene, this alkyl halide becomes this alkene if you do probably something like ethanol and heat. You would get an E1 where the leaving group leaves, a carbocation is formed, it undergoes rearrangement, and then you get an elimination. And then you can cleave right here across the double bond and an oxygen here and an oxygen here. And that gets you your final structure. Okay, sorry I went through that faster than normal. I just really want to make sure you guys have this for your exam tomorrow. Good luck in all your studying, and I'll see y'all for your exam.